talked about the components, header processing, table lookup, header read, queuing of packets, and we talked mainly about the queue placement. And we talked about the size of the lookup and the size of the queues and all that. Okay? And we seen the difference between placing the queues of the input versus placing them on the output. Okay? We see now of this. And then move them here. And then we know that when they are moved there, the implication is that this queue must be running much faster compared to it being placed there. Okay?
So,
Yes, please.
I think you said in the last example, which one is better, IQ or OQ?
Yes, answer it, please.
OQ.
OQ is better.
Yeah. But why?
Sorry?
What's the reason why? OQ is better?
I think it's it, but the reason was.
Yeah, I know you said that.
You forgot.
Yeah.
Yeah, you better remember because you may be asking about things like this. So, performance-wise, it's better to have the queues and output because there is no contention. There is no contention on the crossing of packets here. So packets will be directed to the output. The memory is here. The memory is here. When packets come at different inputs, because they don't get queued here, they will cross directly to the output. So there is no contention over this shared result there. And that will result in higher performance. Please write it down. It's very important. Quick before I move. But the drawback of this is it's quite expensive because the memory must be running much faster. Okay. We show the typical router line card and what does it consist of. So we covered all of this. Just to recap this morning for you guys. We looked at the performance and limitations and throughput, delay, capacity. And we also talked about the need for faster routers and we showed a number of trends, especially that has to do with user traffic, with line capacity, with router capacity, and DRAM access time. And we said that the problem with the routers is actually in memory, because memory consumes a big part of router. Okay. We said that we need big routers for many reasons, especially for the number of interfaces and cost and scale. We covered all this last week. Okay. And we also talked about the big disparity between traffic and router capacities. And we said by this year, in fact, routers are actually 5-fold disparity between their capacity and what they are supposed to process. Okay, and that's why faster routers and big routers and more scalable routers are needed. Okay. We covered all this, and we said that this capacity is mainly because of the memory disparity, of the memory speed bottleneck. Okay, because memory constitutes lots of memory is at the heart of the router. Let's say critical part, because basically a router is a device whereby you put traffic inside the chip and move it out, and that chip is mainly memory, basically. So memory constitutes a big part of it. And that's why we wanted to look at memory in more details. So we say memory. So what is memory exactly? Memory basically, for example, if you look at this example here, and we gave this example of a 40 gigabit per second packet buffer, which is that one, and we are assuming a round trip time of the internet to be 250 milliseconds, which is a typical number. It's pretty much always used as a fourth of a second. For this bandwidth, okay, this speed here, this buffer should be around 10 gigabit per second because that's the rule. This is the rule of thumb. That's the formula. In order to calculate your buffer capacity, it must be bandwidth the input line bandwidth multiplied by internet route bandwidth. And if you are given this type of speed, therefore you will need to have around 10 gigabit memory for that buffer in order to have a reliable communication. Of course, you can have it bigger or you can have it less. Less would result mostly in inefficient network, and that's due to why? I told you last week what this formula, where does it come from? Where does it come from? Anybody tell me?
TCP.
TCP. In order for TCP to work well, you will have to cater that to the buffer. Now, if we assume that we have 64-byte packets, at this speed, here, you will have a packet coming at that bandwidth. Each packet is of that size, so this buffer will have to write packets at this rate. Now, mind you, if this input line here is 40 gigabits per second, in order to sustain a constant bandwidth, or throughput, sorry, this line also is equal to that line. So here 40 gigabits per second, that was 40 gigabits per second. To maintain that, you will have to have packet to be written inside the memory, roughly speaking, every 12.8 nanoseconds. And of course, the packet has to be read out. Or another packet at the head of the queue will have to be read out. So mainly, this memory here, the access time of this memory will be 12.8 divided by 2, in fact. Because writing the packet will take that much, and reading out will need that much. So the memory bandwidth will be 2 double that. In fact, 80 gigabits per second. This memory bandwidth. Okay? The access time of the memory will be this divided by 2. Okay? And now the question is, for a router engineer, what type of memory would you use there? Now we talked about static random access memories and SRAMs. They are known to be fast for this time. They could cater for that time. The problem with SRAMs, they are too low density to store 10 gigabits of data. Okay. The other end of the spectrum, you will find DRAM. DRAM, they are good. They have high density. You can find DRAMs for much more than this quantity in one block. The problem, DRAMs are too slow. So the big question is how to design that memory block. That's the big question. That's the big challenge. Okay? Usually people they maintain, let's say, kind of smart data structures for packets, whereby they store the header in an SRAM and maybe the packet data in a DRAM. There are lots of schemes like that. But here the message for you is to understand that actually buffer memory is quite very critical, and it's important what to pick to have there. For example, if even you pick it to be an SRAM and assuming that this memory will be okay, available to have it in an SRAM size-wise, power consumption is a big deal because SRAM consumes power much more than DRAM. So the question of the memory sizing in a router is extremely important. Here I gave you also a slide about the memory technologies for routing memory technology. So for example, networking DRAMs, SRAMs, or these are called TCOMs, ternary content addressable memories. These are extremely expensive ones, and they consume lots of power. Okay, you can see it there. Actually, it consumes pretty much more than 10 times this one. Okay, and these are some prices, and the max single chip density in one chip. How much you can get? Okay. What else did I talk about? We talked about how fast can you get these, and I think we stopped here last week somehow. Okay. So we talked about the external line to be 64 wide bus. Example: 64 wide bus meaning when you have a packet of 64 bytes. Okay. This 64 bytes could be read here or written in one time because you have a bus wide 64 bytes, so you have lots of lines coming to the memory. Okay, it's wide bus that comes to the memory. Okay. Now that's your buffer memory. So based on the specifications of typical specifications that we are getting from here. Okay. So here we say SRAM is between 2 to 4 nanoseconds. So here we say it's around 3 nanoseconds average access time. From here, the access speed. The DRAM is between 40 and 80 nanoseconds, the access time. So here we said it's around 40 nanosecond access time. We know what the technology is, right? Now we wanted to see how fast can I write packets, or what is the maximum bandwidth I can achieve with these memory specifications. Okay? So if I have an SRAM that has an average access speed of 3 nanoseconds, and I'm having packets here that they come in 64 bytes, in one shot you can write 64 bytes in that memory. How fast can I have my memory? What is the speed they can have? What is the bandwidth that they can achieve with my router? Sorry?
Round trip time. I think this 2 is the round trip time.
This has nothing to do with round trip time for now, to be honest. Because we got data coming to the memory, and I know my access speed to the memory. What access speed that memory has. So I could calculate what is the bandwidth. The bandwidth is the number of packets per second we can read or write. Memory bandwidth is the number of bytes it can read or write per unit of time. Okay? The access speed is the time where you can atomically access a location in the memory. This is the access speed, which is here. Is it clear the difference between access speed and memory bandwidth?
The opposite? Is the opposite?
It's not the opposite. No. Access speed is the speed at which you can access any location in the memory for a unit of data. That's the access speed. The memory bandwidth is how much you can write memory per unit of time, how much you can write data per unit of time for a atomic operation. In this case, if I have...
Because you have 60 bytes, why does?
Yes, that's exactly the point. Yeah.
Okay.
If now, this is just an example. I'm not sure whether technology would allow you to have this wide pass because the chip is not big enough. Now, if you have 64 byte wide pass, you know how many lines you have there? 64 times 8 to write each bit separate. So that will be 512, right? If you got 512 in and 512 out, I'm not sure there's a chip that has 1,000 lines. There are, to be honest. But the layout of the memory also is important, if you see what I mean. Okay? So generally speaking, the 64 wide is not a typical number, it's quite pushed. But you find it in networking technologies like that. For example, computer bus, computer memory. You will not find it this much. It's generally speaking the case. Okay? For the memory of a computer, I mean. Okay? Because usually they are in words. They call it 2-word memory or 4 words memory, whereby you can write 32 bits in one time.
64.
32, 64. That's why they call it 64-bit machine or 32-bit machine. So generally speaking, they are what you call it? They are 5 bytes or 6 bytes actually, or 8 bytes sorry, access. Okay. Now, based on these specifications, therefore, here we are getting a rough estimate about memory operations. Okay. Now. Here what it says my memory operation would take anywhere between 3 nanoseconds to 40 nanoseconds, right? This is my range, this is the interval. Whereby the lowest part of the interval, it means I'm using a very fast memory. The other side is I'm using a very slow memory. Yes, please.
Yes.
Oh, that's all right. Okay, now if we know that if I have a packet that comes, the packet has to be written there and then read out. What does that tell me? It tells me that for every packet that passes through this memory, I will have to have 2 operations, two accesses to the memory. One to accept the packet in, the other one is to take it out. Okay? Because it's called store and forward, remember packet switching? It's a store and forward. You store the data and then you forward it. Store is an operation, forward is another one. Store is writing the packet in, forward is reading the packet out. Is this clear, guys? Okay, now we say 2 memory operations per packet. You write it and read it out. you get two memory operations, what it means? It means you will have anywhere between 80 gigabit and 5 gigabit per second. How do they do that? We are assuming 64 byte packets. 64 byte packets, and each packet will need 3 nanoseconds. Okay? So you divide 64, but this is byte. In order to find it by bit, you multiply by 8. This is 512 divided by 3. Each operation, how much do you get?
Yes.
Wow.
Something.
More. 500 divided by 3 is more than 40. It's 140 or 150. Around. Can you do the math?
Oh.
512 divided by 3. The good people in math. 160 somewhere. 170 somewhere around. Now, okay, this is the time. What is that? That's the how many packets you can have for one operation. But now, if you need two operations, you need to read and write, right? You divide that 170 whatever by 2, because it's 2 memory operations per packet. So that's why you will find it 80 gigabit per second bandwidth. In order for this memory to absorb 64 byte packets at this access speed, and each 64 byte packets must be absorbed twice, 2 operations on each packet. You will need this memory to have a bandwidth of 80 gigabit per second. It should process at the speed of 80 gigabit per second. Is it clear what's said there? Somewhat making sense? Of course, if you have a slow memory, this is the range, because you will use the math for 40 nanoseconds. You will find it 5 gigabit, around 5 gigabit, because you say 170, so maybe it's 80. Clear? So you can see now the choice between SRAM and DRAM is quite different. And there are lots of applications. Application access speed-wise and memory bandwidth-wise. Okay? And access speed and memory bandwidth are extremely important factors. That they determine the memory technology, and they determine the price of the memory, they determine the feasibility of the cloud architecture and all of that. Okay? Now, as I said before, this memory should be large enough for a smooth communication operation in TCP/IP-like communication, okay, or protocol. So buffers, they need to be large enough for TCP to work well. For that reason, DRAM, which is this one, is more suited than SRAMs, because SRAM is not dense enough. It does not have good density to have lots of buffering capacity inside per chip. Okay? So usually people, they choose a DRAM memory. Now, if you choose a DRAM memory, if you link this to what I presented a couple of slides before, you would therefore be more constrained to have a certain architecture of router, namely input queued and not output queued, because output queued requires a fast memory. DRAM may not stand for an output queued router architecture. Is it making sense what I'm saying? If you don't stop me, I assume you are understanding everything. You are stopping me?
No. Yeah, not stopping.
It's all right. You should.
Yeah,
Yes, go on.
Actually, I found that it depends on the router type,
Yeah.
the memory also. But it makes me somehow confused between the access time. Is it here, as you explained, it's called the memory? But what about the access time of the router by itself?
What do you mean the router by itself? What is the access?
Sometimes there is specification, some the access time or scheduled time.
No.
So how this is related to the memory itself? That makes me confused.
In order to sustain a certain bandwidth of the router, the whole operation has to be how to say? The whole operation, the whole pipeline has to be within a certain time. So maybe the memory access time or the memory bandwidth must match the scheduling part, must match the access time per packet in the router. Okay.
So this is more faster, you mean, than the router? It should be.
This is part of the whole router, yes. Depending on where you put it. you should understand the placement of this memory in the router architecture where it is, and that will dictate the time through the router of packets.
And that was related also to the value.
Of course. Okay. Now, faster routers are needed always. So the problem is with packet processing. Okay. So what usually users would like to have, they would like to have more features. Okay. So over time, because you need more features, normally the instructions per arriving byte per packet become more and more, because you will need more processing for every packet. For example, security, deep packet inspection, and all of that. So over time, the number of instructions for every arriving packet, they are growing because users, they are asking for more features. But what happens, in fact, that the number of instructions, in order to make these packets, these routers faster, or in order to overcome the difficulty, you should in fact have less instructions per arriving packet over time in order to maintain a high speed. So this equation is quite hard. You would like to offer lots of features in a router, but actually you are constrained by time. Okay? So in order to maintain a high speed, normally the number of instructions per arriving byte should be few, not many. Because if you have lots of instructions per arriving byte, it means you will waste time. Okay. What else? This slide is trying to give an indication of, roughly speaking, 20 years of evolution in routing, let's say, industry, and it talks about the router performance, so the growth since '92 all the way to 2008, and this is a typical router capacity per rack. Okay. So it goes from 2 megabits per second all the way to more than 11 terabytes per second over 20 years. Okay. Now, if you calculate this average growth, it's around 2.2 per 80 months. Why do we do per 80 months? Because we'd like to compare it to Moore's law. Moore's law has to do with memories. Okay. So it's a little higher than Moore's law, little higher, slightly. Okay. Now, having looked at the main component in the router, especially memory access time and bandwidth, we wanted to see what is needed in order to maximize the throughput of a router, because the throughput is extremely important. It's the capacity, how much data per unit of time the router could deliver for you, and that's the throughput. Okay? So, and why we talk about throughput? Because operators increasingly demand throughput guarantees, for example. Okay? So, to maximize the use of expensive long-haul links, to predict, so you would like to have the throughput, but also you would like to have that throughput guaranteed. You would like to have a router that always gives you a constant throughput. If a router, for example, is having, let's say, 10 interfaces, 10 inputs, and each input must run at 10 gigabits per second, you would like your router to have 10 times 10. Okay, 1 terabyte in this case. Oh, sorry, 100, 10 by 10, 100 gigabits per second. So you cannot say, I have a router, let's say, with 10 inputs. Okay, I'll give a very simple example here. You could easily have something like this. Can you see here, guys? Somewhere. You could have a case whereby you have a router. This is your router. And it has inputs. Okay? This is input 10, this is input 1. And of course it has outputs. Okay? 1 to 10. Now, each one of these is 10 gigabit per second line. Each one of them. Okay? The total capacity of this router is the summation of all its input lines. How much data that the router can process as a whole, right? So theoretically, this one, if each line is 10 gigabit per second, it should deliver to you 100 gigabit per second, right? Is that correct?
Yeah.
Generally speaking, it's not the case. At the best case, the router will give you this, but not all of them will give you that, and that's called throughput guarantee. So this router, in order to guarantee throughput for you, it will deliver 100%, 100 gigabits per second, aggregate throughput. It's called aggregate, the total capacity of the router. But in many cases, actually in most of the cases, is not the case. In most of commercial products, it will deliver to you somewhere in the 90% if you're lucky. Okay. And of course, you can understand why operators, they would like throughput guarantee. So if you go buy a router that says it has 10 gigabit per second interface speed, and it has a number of interfaces, you would wish to have that guaranteed throughput, but it's not the case because it depends on the architecture of your router. If you want to have a guaranteed throughput router, you may need a very expensive one, for example, output queue switch. Okay. And we'll look at these, all right? Now, unfortunately, despite lots of efforts, as it says here in theory, there is no commercial router today that has a throughput guarantee. Pretty much not. The commercial ones, they would always tell you it's 100 gigabit per second aggregate capacity, but in reality, you won't achieve that. It's very similar. When you look at your, I'm sure all of you have connection at home, right? From some operators. When they sell you the product, they will say you get 30 meg per second, right? Did you ever test that 30 meg?
No.
Did you ever reach that 30 meg? That's exactly what I'm talking about. It's never 100%. If you are lucky, maybe. Very rare occasion. Okay? Now, what we looked at the BT at the input, and especially this memory buffering there. That's what I was talking about the SRAM DRAM choice. This slide here, what it's trying to show us, it is trying to show us the whole path of a packet inside the router. What you asked me, Mary. So you said about the access time and all of that, okay? Now, in order to maintain a complete pipeline, normally the access time through the whole router would be the summation of the serial tasks there, right? Now you can see a packet coming through this router, will go through framing, route lookup, TTL processing, buffering as we said before. It will have to cross this interconnect, and that interconnect will need some maybe arbitration, some scheduling, okay? And then when it reaches the output, maybe also it will have some delay there, okay? Now, I think I described a bit this architecture, but now what we are trying to say here is actually if you would like to make your router faster, or you want to maximize your throughput, there are certain parts you will need to improve upon. Okay? One of them is the buffering, where you place the buffering. We talked a bit about that. We are going to talk about it a little bit more. Another part, depending on your buffering, is this shared part, because the interconnect is shared among all the inputs of the router. Okay? All the inputs, they would share this part here, if you have another input here. Okay? I told you last time about data path, control path, and scheduling path. What do they mean? I think we talked about this last week or the week before. Remember that? Remember? You remember guys, somehow? Good. Now, here it says, in order to maximize the throughput of your router, it would depend on the architecture on the switching, which is the switching. Pretty much, it refers to the buffering and the interconnect. This is the switching part. Okay, where do you place your buffer? It would depend on that architecture. Is it input queued? Do I put the memories at the input side before the interconnect? Do I put them after the interconnect? And that's called output queued. Or maybe do I put them before and after? Do I split them? That's also another type. Or maybe should I put them inside the interconnect? That's also even another architecture. So depending on where you place your buffering with respect to the interconnect, you may have an idea on your throughput and the cost of your router and all of that. Okay. So it says it depends on the arbitration of scheduling algorithms within the specific architecture, and it is in fact a key to the overall performance of the router. Okay. Now, for example, here you can see your inputs are here, your outputs are there, and we've got the queues at the output part, right? So this architecture is OQ architecture, and we talked about this before. And again, we have the input here does not have any buffering because the architecture is output queued. You just do lookup, and on the fly you pass your packets. and this is a scenario where you get different packets coming here, and I'm making the worst case scenario where this header, the source address or the outgoing interface is always the same somewhere here. Okay? Okay, so all these packets, they would like to be gone there. If these packets come at the same time here, okay, they come at the same moment, and these are different interfaces that they don't know about each other. And because there is no buffering here, so when these packets come here, they get looked up, and this operation is the same for each one of them, so it gets finished at the same time. So these packets, they will be crossing this part at exactly the same moment. And they will be crossing this part at exactly the same moment, and they will be written here at exactly the same moment. Okay? So you should have enough bandwidth in this memory to absorb them at that speed they come in. Is it clear? And that's why here it says this memory, it is n times the line rate. The bandwidth of that memory must be n times. Why n times? We are assuming this is n. Is it clear? So if this line rate here, as it says there, is 10 gigabit per second, this memory here must be n times 10 gigabit per second in order for this architecture to work fine. I hope it is clear. Is it? You don't understand also this is a bus. This must also work n times the line rate, the interconnect. Because at some point, the packets will be crossing a certain bus there, and that bus clock must be this. So it should pass the packets much faster than they come in order to sustain them, reaching that numerical speed. Clear? Good. Now, if I move these guys from the output to here, it becomes another story. Now, when packets come in, because the memory now is at the input, and they don't have memory at the output, they cannot afford to send more than one packet there. If I send more than one, they will collide, there will be collision, and one of them will be lost. So therefore, I will need somebody sitting here or sitting here, sitting at the output, to look at all the queues, to examine the destination interface of each packet here, and make sure that there are no two packets going to the same output. That's called arbitration. Is it clear? So if I got all these packets, all of them they want to go there, only one will go. Because if I send more than one, they will be lost. What happens to the rest? They get queued here. Clear this? Now, if they get queued here, can you tell me what's the memory bandwidth requirement?
N times 9?
N times the line rate. N times.
1 time rate.
1 time the line rate. More.
Maybe in addition, also the rate by itself.
What do you mean by the addition of the rate by itself?
Yes, n times the rate and the rate also.
Ah, the right.
Hmm?
Right or rate?
The rate, no,
The rate.
Yeah.
So you say n times.
Mhm.
One said 1 time. My answer is 2 times the line rate.
Yeah.
It's 2 times because you don't need n. You don't need n. Because this is physically simple. So you will need to write the packet in and read it out. So 1 time to write, 1 time to read. It's exactly what I showed you here. Let me remind you. You forget quickly, guys. Here, remember? 2 operations, 2 memory operations per packet. I presented this here. Okay? So, the memory bandwidth for an input queued switch is 2 times the line rate. Now, this is very important. Why? The memory bandwidth of this router, of the input queued, you're not agreeing? No, please, if you're not, tell me.
No, it's good, it's good, it's good.
Are you sure?
Yeah.
Man, another time, are you sure? Good. Now, the memory bandwidth is 2 times the line rate. That's the memory bandwidth of an input queued router. This is to be compared to this architecture, this one, which is n times line rate. So the bandwidth of this memory is not only function of the line rate, is also function of the number of inputs.
What this one is not 2n times line rate.
Sorry?
This one is not 2n times.
Why it's not 2n?
Because you need to read it out, you know?
You will need to read out 1. The correct one should be n plus 1, not 2n. Because you write n, but you read 1 out. 1 packet goes out.
Gotcha.
So it's n plus 1, you're right. But I'm leaving that plus 1 for later, I'll tell you why. Okay. So, now the key difference between this architecture and the previous one, please note this L again. So, the memory bandwidth of this architecture is function of 2 variables, the memory line rate plus the number of inputs, and they are multiplicative, n times. Okay, so that's why the scalability of this memory is quite limited, because it's function of 2 variables, the input line rate plus the number of interfaces, whereas this one here, it's 2 times the line rate, and 2 is constant. If you see the difference. So 2 times the line rate is much more scalable speed-wise than n times the line rate. Okay? Because it scales slower. So you can afford to have it faster at lower costs. Now, here, you actually manage to have this low memory, which is cheaper one, at what cost? At the cost of adding another circuit there that is called arbiter schedule. So now you will need to arbitrate. And arbitration, it means complexity and it means especially time and it means performance. Controlling the delay of packets. Extremely important, I would say. Because before, I did not care about packets. When they come here, they go there. What did I pay? I paid an extremely fast memory there, extremely costly one. I did not care about the packets. Actually, it's a very good architecture. It works perfectly fine. Things are going very fast. But I paid lots of money because I will need a very expensive memory there. Now, if I don't have enough money, or if technology does not allow me to have this fast memory, I have no choice but placing the memory at the input. Why? Because now I can afford it, cost-wise or even technology-wise. The speed of the memory is low in this case. Okay, it's affordable. But this implies that the performance of my router is not as predictable as the previous one. Why? Because now, depending on my traffic, I may end up with packets being queued here for a long time. So it's much harder to control their delay, if you see what I'm saying. Is it clear? Because the whole story now will depend on this element that is called scheduler there. Okay? Because it's this circuit that solely decides who goes first. So unless you design a very good one there, very good arbiter, you may end up with low performance router. Okay? And this actually gives you the two different architectures, input queue, which is this one, and output queue, as you can see, the queues are there, which is this one. So these are the two basic known techniques. Okay? Now, I'm going to give you an example, maybe later actually. So this is this is called simple model of output queue switch, exactly what I showed you before. So this is a router with, let's say, 4 links, but they have a line rate R bits per second, okay? And these are different memories, but they are physically different on different interfaces. Now, theoretically speaking, worst case scenario, I could have these dashed lines. It means, theoretically speaking, every single memory could potentially receive traffic from these different inputs at the same time. Yes, please.
Why the input would be the same output? I mean, one link one will receive input from link one.
Sorry, why? What?
Why the link one output is gonna receive input from its own line link?
No, it's not receiving from its own line. It will receive from here. Also. You see?
That's like 4. Yeah, they receive 4 from 4 outputs. So I mean the same link is gonna be output and input.
I did not understand your question.
Yeah,
You are asking. Say
the
again.
number of lines maybe. We find this is the right, but what about the input of lines entering the buffer? This is here.
I mean, why the output should be the same as the input?
Where did you see the output the same?
Now the link one, for
I
example,
mean
the
here.
top. The top, the link one ingress
Yes?
is going to the link one output.
Where it's going to link one? Where did you see it?
I don't know, there is
You mean here?
Yeah, now
This one?
Yeah.
But there are different. So this here, this output link could also receive from 3 other different places.
That was why? I mean, in which case, like, you're gonna forward the packets on the same link?
In which case?
Yeah.
In many
I mean,
different cases.
I mean, this is maybe stupid, no? I mean, you receive a packet from one
It's not the
from
same
one
link, no.
interface, and you're going out from the same interface.
Yeah, but you could be going somewhere else because the same interface does not mean it's coming from the same place. It's just a name of interface. Okay?
Yeah.
So it could no, because this is physically 2 different lines. They are multiplexed on the same cable, but does not mean they are coming from the same physical other place. I see what you are saying. I see exactly what you mean. So it does not mean that this actually coming from another entity that is exactly the same. It could potentially, because these links, in fact, they are multiplexed. So you could multiplex 4 lines into one, whereby these 4 lines, they are coming from different sites. And usually they do this to aggregate. So for example, this link could be 10 gigabit per second, whereby you multiplex 4 2 gigabit per second small lines, smaller one, and they get multiplexed into bigger one. So it does not mean input 1, output 1, it means it's coming from the same source.
Okay.
It doesn't mean that. Okay. Because yes, in that case, it would not make much sense.
Yeah, that's why I
Ah.
asked the question. Thank you.
But anyway, so here, because each memory could accept from potentially any input, maybe the good question you should ask me, you should know that R there. So the link rate here and the link rate here must be equal. Let me ask a question. If the link rate R here is less than this one, what does that mean? Anyone can
You should use the packets.
But
We lose some of the packets.
You lose some of the packets. You
must be the packet loss, as you say.
say again?
Packet loss. Some packets will be drops.
Why?
Because the output link is
It's slower than the input, and you will end up with a big buffer here. So unless your buffer is infinite, you will lose packets.
So is that theoretical? Because
not.
I understand the throughput here is the same as the rate, and in the practical the throughput is not the same as the rate, because when we have a specified rate for the link, and when we get the packet, it's not the same. It will be because of the delay or because we lose the packet, so it will be lower than.
You mean the throughput of the router?
Yeah.
Throughput of the router, first of all, is a percentage. So we refer to the throughput, generally speaking, as a percentage in terms of 90%, 100%, which means how much data you can get per unit of time here with respect to how much you can get there.
Yeah.
Okay?
Mhm.
So that's the throughput mainly, and it is usually less than 100%. Usually.
Yeah.
In the best case scenario, it is 100%. The best case scenario. Now, I'm talking about something else. If you are having a lower egress speed, that would mean actually this system is not sustainable system, because over time, because your service rate is smaller or less than your arriving rate, and your system is not sustainable. So yes, please.
The same thing in the case if we have lower output and lower rate in the output. Does the router will discard the packet
This is a point.
or will we delay or will we delay in the router to deliver the
Yeah, but no
the
matter
packet
how
to the output?
over time, no matter how much you delay it there, your system is not sustainable. Because now it's a question of time. How long will you delay to absorb that difference? So over time, this router is not delivering 100% throughput, so it's not a sustainable system. So generally speaking, when you talk about a routing system, the output link must be equal to the input link at the same interface, as you said before. So the input output here, at this point, what you get in must be the same out at that point, at the interface. Okay? Clear? And this is the model. This is exactly this model, whereby you got your outputs here, which are, sorry, let me go back, which are these ones. So now, if you get, in this case, you could get any combination of packets. The traffic here is unknown. Okay? It's It's instantaneous traffic that is coming into node, into route. In this case, it so happened to be that we have 2 green packets and 1 blue one, which means these 2 packets, they are wanting to go to the green output, these ones go to the blue one. And that's how it works, precisely. Okay, which means this memory there is able to absorb 2 different packets, but theoretically it could absorb the 3 of them. And that's why this memory must be running at least 3 times or 4 times as much as each inputting. Okay, it's n plus 1 times the line rate. N to absorb them, 1 to read out. Okay? And this is the same model, but I'm trying to talk about its characteristics. So arriving packets are immediately written into an output queue without intermediate buffering. There is no buffering at the input. The flow of packets to one output does not affect the flow to another output. This is very important, that second point, because packets that are going here, they don't really affect packets that they are going here, because the memory is fast enough. If it was input queue, it would be different. Okay? An output queue which has the highest, I would require that you highlight that word, the highest throughput and lowest delay amongst all architectures. You cannot achieve better delay than this architecture in a router architecture. Okay? What else? The rate of individual flows and the delay of packets can be controlled. This is a topic that we're going to cover at some point later. Okay? So this architecture is the one with the highest throughput and lowest delay or controllable delay. Now, practically speaking, this architecture is very expensive due to the memory requirement. So what happens, because it has the highest throughput and lowest delay, and because it's unpractical, router industry, they employ smart engineers and they tell them, could you design for us a memory architecture that resembles this, but not at the cost of this? If you see what I'm saying. Can you design a memory, a router architecture with memories that are cheaper than this, but hopefully the whole router behaves as if it is like this? And that is called output queuing switch emulation. Can you have a router that behaves like an output queued router without having the router to be actually output queued router? Is it clear what I'm saying? We will cover maybe half a lecture about what I said now in this sentence. How you emulate an ideal architecture with slow technology. That's very important. Now, there is another technology, or there is another architecture that's called shared memory router. Can you see the difference between this and this? Anybody can tell me the difference? It's very similar to the first one. Very similar. Yes, guys, please wake up.
Single memory device.
This is a single big memory. The previous one are separate memories. That makes it completely different, I guess.
Because everything is here.
So what is the bandwidth of this memory then? Don't read the notes. Talk to me. 10 times 3. Where the 3 comes from? 4. No, in this case, no, I'm talking generally speaking. In this case, I'm giving n, no? It's not 4. This n times the line rate, n times the line rate.
For read and write. And the 2.
Tell me the number.
2n.
2n.
Yeah. Because we need to read and write and the n. But in the other case, it was separated.
True.
Yeah.
So you will need to read at most n of them and write n of them and read n of them at the same time, and that's 2n. Right.
Line rate?
It's 2n times line rate. Don't worry, it's written somewhere. We'll get there. This is it. Actually, it says there. So this is the memory bandwidth. So the output code is n plus 1, and the 1 is for the right there, as you mentioned before, times r bits per second. The shared memory is 2n bits per second. Okay, these are extremely important characteristics. Okay. What else? This is the model again. I don't know why I'm showing this, but just to illustrate. Okay, so that's where the n+1 comes in. This example, this animation, it's showing you, oops, this one, it's showing you the n+1. The n is the right axis, which is this one. This is the n. N meaning I write 3 packets. The +1 comes from this animation. Oops, here you go now. That's the +1. In an output code switch is always n+1. So n to write all of them, the +1 is to read one packet out because that's r equal to r there. Clear? Good. That's the same thing again. Now, these two previous architectures I showed, they are known to be extremely complex and expensive to build because of the memory bandwidth requirement. As you can see here, if this n grows fast, for example, if I have a router with a high number of interfaces, let's say 256 interfaces, and each one of them is 10 gigabit per second, this memory bandwidth to be for an output switch will be n+1, which means 256 plus 1 times the line rate, 10 gigabit per second, 257 times 10 is 257 gigabit per second bandwidth memory, which is impossible to build. So that's why the memory bandwidth is a problem, and therefore the architecture is a problem. And therefore people started looking at the input cloud switch one that I showed you before. In an input cloud switch, the memory bandwidth is just 2R. You see? So it's not function of the input line, of the input numbers. Previously it was a function of n, the input number. Now it's constant times line rate, so you can control it in a way. It's more affordable, the very least you can say. Okay? However, there is a big phenomenon here. When you use input FIFOs, FIFOs is first in, first out. I hope you understand what FIFO is. People do. Input queues, it can result in what is called head-of-line blocking problem. Head-of-line blocking, I'm going to explain what it is. Sorry. Now, this is my architecture. Theoretically, this architecture, if it was an output queue switch, if these queues were placed there, my theoretical throughput would be 100%, right? What I get in, I get out. Normal. Normal. However, when I have input queues, in this case, this architecture cannot deliver to me more than 58.6 throughput. It has a very low throughput due to what is known to be head-of-line blocking. I'll explain what a head-of-line blocking problem is in a second. Okay? This is head-of-line blocking problem illustrated. Imagine that I have my traffic column like this. Okay. Now, mind you that the color of the packets will determine their output interface. So I got 3 outputs here. A green output here, black output, and the red output. Now notice in this scenario, because these queues are FIFO queues, first in, first out, so this packet will never get served unless this is served first. The same happens here. The green packet will never be served unless the red packet is gone, because it's first in, first out. Okay. Now, in this scenario, because I have input queue switches architecture, the queues are the input. Okay? How many packets will get out? Just one. Why? Because all of them are red, and here I don't have buffer. So I cannot absorb more than one packet with the line rate. So only one packet from these 3 will go, and the other 2. Now, which one will go? The arbiter will decide which one. But the fact that in this type of scenarios, third, only one, I would say. But in this case, it's 3 inputs, so 1/3. Only one packet will go, and the other 2 will be blocked. Now, as a result of this scenario, this output and this output, they stay idle, even though they got traffic of the inputs going. So we say that this packet has a head of line blocking. It's blocked by the packet ahead of it, and as a result, it was deprived from its otherwise free output. So this output stayed idle. We lost connection simply because there is a guy who is accidentally in front of another guy, not blocked it. Okay? So this is what happens. So the packet, they move, and you can see that none of these have moved. Because, so we picked this one to go, but that one came from here. This did not go, this didn't go, and none of these did go. So that's the head-of-line blocking problem. Is it clear what head-of-line is? Now the question is how to solve this. Because this head-of-line results in a very terrible low throughput. Okay? The head-of-line is exactly equivalent to this for those of you who drive. To understand what head-of-line is. So imagine that there is this car at this crossing next to the university, and it's red line in front of it. Civil engineers, they thought about this. Car traffic people. So this car coming behind it, the blue car is wanting to turn right. Okay? Although it has free passage here, it cannot turn. Why? Because it's blocked by the red one, which is blocked by traffic light. Car traffic, they solve this by having separate lines. So what happens? The car will come, it's turning, it will not wait for this guy who is blocked. That's exactly the same thing what's happening in traffic design. So this guy will go. This is what's happening in car traffic, right? The same has happened for route design, actually. So they designed separate lines per destination. If you see what I'm saying. That's exactly what it is. And that's called virtual output queues. Okay. So virtual output queuing is at each input port, there are n queues, each associated with an output port. Which means I maintain an output destination per input. Okay? But you retain the constraints of an input queue switch in the sense that only one packet can go from an input port at a time, and only one packet can be received by an output at a time. Okay? So what happens basically that this architecture, I added virtual lines, but I retain the scalability of the FIFO input queue, which means the bandwidth stays the same. The memory bandwidth per interface is 2R. Okay? Although I added logical lines, I will show you here. But it eliminates the head-of-line blocking. So, and I wanted to show you Now, instead of maintaining one FIFO queue per input port, I'm maintaining as many FIFOs as outputs. In this case, I have 3. I'm maintaining 3 different logical lines per input. If I had 4, I would maintain 4 per input line. If I have n, I would maintain n. Okay? So at each input port, I maintain n virtual queues. Now, why n virtual queues? So that when I have traffic coming in, I will queue traffic per color, per output. Is it clear?
Yeah, just this n depends on what?
N depends on the number of outputs.
On the number of the output.
N is the number of outputs. Actually, it's the number of inputs, outputs. Although theoretically speaking, the number of inputs may not be the same as outputs, but generally speaking, it is. Okay? So here I would maintain a line per output. Clear? This is your traffic now coming. Notice now that there is no 2 different colors at the same line. Now, if you got a packet here, or let's say a packet here, and it's blocked by another packet ahead of it, it must be blocked by a packet that has the same destination. Does it make sense? Now, this architecture, although we added logical lines, we maintain the previous constraint in the sense that I must mind you actually here, the animation is not 100% faithful to the reality. When you do like this, you notice that packets here, you see 3 packets, for example, go there, coming here, Per unit of time, I will have a maximum of 1 packet coming to any of the queues. I cannot have 2 packets coming here, because it's line rate R. Is it clear? Important, very important. So I cannot have at any moment of time, for example, more than 1 packet coming to this interface. It should be a line here, a line here. Okay? I could have maybe a packet coming there, or packet coming here, or here, anywhere, but not more than 1 coming there.
Why?
Sorry?
Why not more than?
1, I mean the line rate. So I cannot have more than 1 packet per per rate of the input line. So if I have 10 gigabit per second line, I cannot have more than 10 gigabit coming divided over this and this. I'm constrained by the line rate. So if the line rate is 1, I will have maximum 1 coming here and maximum 1 going out there. Making somehow sense what I'm saying? The message here, although I have different queues per input, I can at maximum have one of the queues receiving packets per unit of time. Okay? The same happens here and happens here. Now, consequently, I cannot send more than one packet from every interface. So although here now I have different queues per interface, at maximum I will send only one packet out. Because at maximum I receive one packet in, at maximum I send one packet out. And that's where the 2R comes from, in order to maintain the low bandwidth. If you see what I'm saying.
No.
You did not get it.
No. Why? If you prefer 3 packets from different outputs.
Say again?
If you prefer 3 packets for different outputs, because like they're waiting for it, you can just for 2 of them, no?
If I have 3 packets from,
In the buffer.
yes?
You can have 3 packets in the buffer for 3 different outputs.
You mean here, for example, this case?
Yes, yes.
Yes?
This is possible. So why in one time you cannot forward all this?
Potentially I can send the 3 of them. But if I send the 3 of them, it means my read rate outside of this memory should run more than 2 RPM.
No.
No, but I would like, sorry? Do you say yes or no?
Yeah.
Big-
Should be.
Should be more.
Yeah.
Therefore, it's not input queued switch router. Because an input queued switch router must have 2R memory requirement. Of course I can send these 3 at the same time, of course I can. But if I send these 3 at the same time, therefore I'm an output queued switch router. Now I'm designing an architecture that eliminates the head of line problem, yet it has a memory bandwidth of 2R. This is the key point. Is it clear, the message? Of course, potentially I can design a memory that can send 2 or send 3 or send 100. But therefore, am I rich enough to afford it? No. I would like to keep the constraint of low bandwidth. Okay? Now, this architecture, what it is saying, virtual output queues, it means, as opposite to this one, oh, boring story. Where am I going back? As opposite to this one, mind you that now, before we picked the red packet here, right? That red packet was picked by some circuit sitting here called the scheduler. Okay? The scheduler looks at the head of the queues. Okay? So in this scenario, the scheduler who is sitting here, it sees only who is sitting at the first line. It does not see the people behind it. So the scheduler here only sees this red and that red that picked and that red. It does not see green, does not see black, does not see green. The scheduler always sees the head of lines.
Does it mean all of them have the same address key stage numbers?
Of course, because they are red in this case. Yeah? So the scheduler sitting there will always see the head of the queues. Now, as you can see, these red, the green, and the black, they are hidden to the scheduler. And that's why he cannot see them, because it is a FIFO architecture. Now, going to this story here, let me move back quickly. Now, you see, if I have a scheduler sitting here, because it can only see the head of the queues, it can potentially see all different colors and can pick up. Now, the key question that results out of this, it is nice to have this architecture, but now the complexity moves all together to this connection here, which is some guy sitting somewhere there, and it is called the scheduler. How to pick packets from different inputs, going to different outputs, such that you maximize the number of connections. If you see what I'm saying. This is the problem solved by the scheduler. So if you have a circuit sitting there, that circuit would answer the question to you, can I, given a certain matrix, certain inputs go to certain outputs, can I maximize the number of connections between inputs and outputs such that I pick at maximum 1 packet per pool, per input port? Is it clear the problem how it is defined? Can you maximize the number of connections such that I will pick at maximum different color per input? So if I pick a green from here, I should make sure I should not pick it up from here. Why? Why cannot pick two green here and here? Because they will end up going to the same output and that violates the constraint. So the scheduler must pick at most a packet from each interface such that each packet is different from the rest color-wise. Okay? And it must coordinate that. Of course, at the same time, it should maximize the number of packets. It should send as many packets as possible, which means spreading the destinations. All right? That's the job of the scheduler. This circuit is not as simple to design, and mind you that these circuits are in hardware. There is a circuit, there is a laser that does that. It's not quite simple to come up with a circuit or an arbiter that is good enough for this architecture, and therefore the whole deal of this architecture, which is the majority of routers nowadays, they implement this, the key block is the arbiter, because it's very traffic dependent. Okay? So this is one scenario, okay? And here it says if I have input queued router with virtual output queues here, I could potentially have 100% potential. Okay, guys, sorry, I did not stop. I will stop in 2 minutes. Sorry, we moved on. Let's continue these 2 slides before we move there. Okay, so if I have VQs, I will have 100% throughput potential. This solely depends on the scheduling algorithm, on the arbiter. If you design a good arbiter, you will have 100% throughput. If you design a not good arbiter, you will not have 100% throughput. I must say that when it comes to your project, guys, most of the projects is how you design a good arbiter for this type of architecture or another one. That has to do with architecture. Most of it, okay? So, and that's the scheduler there, so it says it can be quite complex, and this is a way of modeling the power out. These are the outputs here, designed this way, okay? Memory bandwidth are there, and this scheduler must pick at most 1 packet from each interface here, and send at most 1 packet to another interface, such that it maximizes the number of packets crossing this path. That's the job. Okay? Sorry. This architecture here, this is a crossbar. Now I'm talking about a completely different architecture. I just wanted to show you a different architecture. This is called buffered crossbar. A buffered crossbar is a crossbar that has buffers inside. This is a very popular architecture as well. Now, if you have a buffered crossbar where you add buffers there, the scattering problem completely becomes different discussion. We will have a lecture on this, complete lecture on this architecture. Now, when you have buffers here, this buffer, for example, that one, that very one here, it holds traffic coming from here and going here. This buffer here, it's matrix, it's an n by n matrix. So this entry here is called 3-2, which means I would receive traffic from the 3rd input going to the 2nd output. It's matrix. If I have n inputs, 4 by 4, I will get 16 buffers here. Each buffer, that's more one there. It's solely linked to a VLQ. So for example, this buffer here is buffer number 3 in input number 3. Or it's coming from input 3 going to output 3. Coming from input 3 going to output 3 will be this one, the red one. So that will hold packets from the red one. And if you treat it per column here, you will find packets in this column, they are all red. So these buffers here, they are holding traffic that's going to output 3, which means potentially every 3rd input, every 3rd VAQ in an input. Is it making sense?
Where is the role of the scheduler?
Here?
Of the arbiter?
Of course it does. There is a big role here. Which one you pick first from this line? But now the arbitration is quite different. Now it's a distributed arbitration, completely distributed. It's not like before, whereby you solve input and output at the same time. We will have a complete lecture about this, about arbitration and the design of this. It's quite different architecture than what I was showing you before. I'm just trying to show you different architectures, like I said, output queue, shared memory, input queue. This is a buffer cross-bar. Okay? I'm not going much into the details of this now. I'm just telling you the architecture how it works. We will get back to this for a complete lesson. Now, what am I going to talk about? This is a comparison of memory speeds for a 32 by 32 switch, packet size 64 bytes. So if you get a line rate, different line rates, based on your architecture, you should be able to work out the memory bandwidth and the access time per packet, which we talked about. Your memory bandwidth here, we said a shared memory is 2NR, right? 2NR, N is the number of inputs, here it's 32 by 32, so the number of inputs is 32. The line rate is 100 megabits per second, right? So the memory bandwidth for a shared memory, because 2NR will be 6.4 gigabits per second. The access time per packet, what is that?
Depends on the packet.
Is
size.
packet size over memory bandwidth. It's packet size over memory bandwidth. You may write it down, it's not written there. But this equals the packet size divided by memory bandwidth. So from this here, you can, that quantity and this quantity, you can find out how long do you need to write that quantity of data, which is access time. Now, if you can see the input queue, there is a big mismatch. Because it's 2R, the input queue architecture, the memory bandwidth is 2 times R. So it's 2 times 100, it's 200%. As you increase the line rate, you will see different numbers here. And this is quite very unfeasible, as you can see there. I'm just giving you some examples. Is it clear how you compute this?
What is the output queue also?
You can add it yourself. It's an exercise for you to do it tonight.
Another thing, I just want to know
An output queued switch is n plus 1 times R.
Yeah.
So in this case, it's n plus 1 times R. It's 3.3 gigabits.
and then we divide to and the arbiter time, how to find it, I don't know.
I'll tell you. Now, these are some switch fabric chips, commercial ones. So it's there for you to have a look at. So what company do this? So there are a number of different companies like IBM, Broadcom, and a number of them. So what do they provide as name of chipsets? Switching capacity, power, prices, and switching architecture. So as you can see here, a number of architecture are crossbars. Most of them, they will be crossbar, I guess. So the last 3 crossbars, here maybe the majority are crossbars. A couple of them are buffered crossbars, and the other ones are shared memory. I think 3 or 4 are shared memory. So these are the most maybe popular type of architectures you will find, okay? Just for your reference. I think this is the last slide of the previous lecture. We are a little bit late in time. Would you like to have some rest, or shall we continue and stop 10 minutes before? What do you prefer, guys? Sorry? Shall we continue and stop at 10 to? Which is better? 15 to. I will let you go 15 minutes before. Okay. There are some notes there for you. I'm going to move on to the next lecture. So you can have the notes there. They hope they have the material here. because this is the same. Oh, this is the interconnector. The interconnector is here. Those ones here. Mhm. Hey,